prefer the student to be here, but well, you can see it on YouTube. And just in case, there is a place where everything related to this course will be put. I hope it's seen. So I'm going to put there the exercises, the lectures, and so on. But I think it would be better if there were somebody to ask me questions. And to solve the exercises, because there will be some exercises for class. No? Okay. At that point, I should ask you whether you know all this preliminary thing and whether I should tell you the definitions or not, but I can't. Okay, so the subject of commutative algebra is commutative rings. Commutative rings and objects such as ideals, models, sometimes complexes of models over commutative rings. And this is more or less algebraic geometry, in the sense that algebraic geometry deals with the same subject, commutative rings, but from the geometric point of view. You cannot study algebraic geometry without commutative algebra, and you cannot study commutative, well, you can study commutative algebra without algebraic geometry, but it's harder because most people, the intuition for most people is based on geometry. And then you have algebra, which is harder to understand if you don't use geometric point of view. On the other hand, commutative algebra has applications not only to algebraic geometry, but to number theory. It's really important. And to some other subjects, such as complex analysis, homological algebra, and some other things. For instance, if you look at the proof of Wiles of Fermat-Gray theorem, half of it is commutative algebra. It's deformation theory for commutative rings. Okay, so this was the introduction for the subject. Now the preliminaries is a standard algebra book. There is, in this page, there is an announce for these lectures, which contains literature. So you can, but this every book on algebra will work for most preliminaries, such as groups, rings, fields, vector spaces. This is algebra. Also, at some point, I will use basic set theory, but it's only in the first lecture. I would use Zorn lemma. And all rings are commutative and with unity. All rings are commutative and with unity, and this is the assumption which is every time is taken. Okay, so the plan for today's lecture is I start with algebraic sets. So the plan is more or less the same as the first lecture on the algebraic geometry. Algebraic sets, ideals, and Hilbert-Nussstellensatz, which allows us to connect commutative algebra and geometry. I will use a shortcut towards Hilbert-Nussstellensatz, which uses ground field C only. So when you do commutative algebra, typically you don't assume that the ground field is C, and quite often you do with rings over Z or finite field over periodic rings, periodic integers, over arithmetic integers, and so on. But since I would prefer to do to use geometric intuition, I'm not going to do that. So for me, all rings are algebras over C. This is the running assumption. Of course, you can modify all arguments in the end. And in fact, in the end, we will have another proof of Hilbert-Nurstein Satz, which doesn't use C. You can use it over every ring. And in fact, this proof can also be adapted for all other fields using some standard arguments from model theory and logic, which is not hard. I mean, these arguments, logic is hard, but this argument is not hard anyway. So it's a baby version of the Hilbert-Nurstein Satz, which I'm going to prove today. So for a moment, I define algebraic sets. Definition. A inside Cn is algebraic if A is common zeros, is the set of all common zeros of a system of polynomial equations. And now we are considering the ring of A. This is polynomial functions. On A. So you should think about A as about your manifold where you work, like variety. And the polynomial functions are your functions. For instance, this is very similar to how you work with differential geometry when you consider smooth functions, or with complex manifolds where you consider holomorphic functions. But this is the geometric part. The algebraic part is that all rings we are interested in have this form, at least when they don't have nilpotence. And typically we won't be interested that much about rings with nilpotence. But this is, of course, corollary of Hilbert-Nurstein Satz, so I'm going to go slightly backwards in the sense that I start from geometry and go to algebra then. I don't know. For me, this is easier, and since there is nobody to contradict me, this is how we will do. Next time I will tell about a couple of words about categories. Today I'm not going to do that because this is like introductory talk. But we're interested in maps from algebraic sets to algebraic sets. A to A prime, a morphism, or algebraic map. Map from A to A prime is just polynomial map. So both of these spaces are inside Cn. Well, for different dimensions, of course. And then the map from this to that is given by polynomial functions like this. So next time I will explain what is categories and how you consider that as a category of affine varieties. Okay, so the first step in algebraic geometry is study of affine varieties, which I have defined as algebraic set with algebraic ring of algebraic functions on it. So definition, algebraic variety is a subset Cn, algebraic set plus ring of algebraic functions on A. Well, you can consider just a subset of Cn, but then the interesting thing is that you can forget that it sits in Cn. So, of course, we will be, as you are, I mean, it's not interesting to fix embedding to Cn. It makes very little sense because then you want to take things like products, and then keeping track at the embedding to Cn is always bad. For instance, it's bad if even in differential geometry, you don't usually consider manifolds inside Rn. Usually you consider manifolds which are abstract. So this is why we're interested in classes of algebraic varieties up to isomorphism. So what is isomorphism? It's a bijective map from one algebraic variety to another, which is given by polynomial, and the inverse is also given by polynomial. So definition, A inside Cn, A prime inside Cm, algebraic varieties. Phi from A to A prime, psi from A prime to A polynomial maps. And phi times psi, psi times phi are invertible. I mean inverse, identities. So these two maps are identity. And when I say identity, I should specify that it is identity not only on the sets, but also on functions. Otherwise, you can have things like, well, it's better to specify that it's identity on functions. So the algebraic, this map also, I mean, you can take pullbacks of algebraic function from A to A using this map, but it should be identity. But this, here you don't need that. But like in more complicated versions, you really want to all your structures to be compatible with your maps. Okay, so algebraic geometry deals, at least affine algebraic geometry deals with the algebraic varieties up to isomorphism. And then the catch is due to Hilbert, Emmy Noether, some other mathematicians as well, who realized that the category, the affine variety is the same as its ring of polynomial functions. So today I'm not going to explain that in more detail, but I'm going to build up to this idea slowly. And you can solve problems of geometry algebraically. Like you have a problem, you have some geometric intuition how to solve it. But geometric intuition is very hard to apply in practice because, I mean, in practice you need to write down something, and geometric intuition is a picture. Then you use algebra to write it down, and conversely, if you have a problem on algebra, you can apply geometric intuition, solve it, and write down the proof algebraically using geometric intuition. There's a picture illustrating that. It's from Solve and Coagula. You can think of geometry and algebra as two sides of this picture. It depicts two approaches to chemistry in medieval alchemy, and which are sort of clearly the same but opposite. I think black is coagulant, white is solve, but who knows? Probably algebra is. Well, we can discuss that later. Okay. Now maximal ideals. I'm sorry if it is very trivial, but it's hard to know what is trivial and what is not unless there are students there. So, ideal inside a ring subset, which is closed under addition of adding, closed under addition, and also under multiplication on elements of A. So for each x inside I, each A inside the ring, x, AX belongs to I. In particular, if your ring is an algebra, it's in a vector space over a field, the ideal is also in vector space over the same field. What is important, and this again basic algebra, that a quotient set, quotient space or quotient group, additive group, is also a ring. I'm not going to explain this. This is an exercise. I hope that everybody knows this. Okay, now maximal ideal. I is maximal ideal. If for each I prime containing, yes, the important thing which I didn't tell you, it should not be equal to A. There are two approaches actually to ideals, two conventions. Sometimes people assume that A is ideal, sometimes not. The question is whether 0 is a ring or not, because 0 has not unit. So for us, 0 is not a ring, but of course, if you admit rings without unity, then it is a ring. So for this approach, I will use this convention that the ideal can't contain unity. Okay. So if for each ideal I prime containing I prime is equal to I. This is what is maximal ideal. Okay, there are two observations. First, yes?
It's a definition of maximal ideal. It's nitpicking, but you probably want to exclude, you want it to be proper.
Yeah, yeah. So I don't allow for ideals to contain unity.
Ah, okay.
This is what I just told.
0 is maximal ideal.
0 is not maximal ideal unless you have a field.
But in a field?
In a field, it is a maximal ideal, definitely. I mean, I think this is common for all conventions, even those which, when you consider are ideal in itself, which I don't. Okay, so first trivial observation is that remark or exercise. Here I should just ask some student to solve it. But anyway, so you have, suppose you have A inside a ring R, and A is not invertible. Then A is contained in an ideal. So we always have these ideals. They are not equal to A. Our I is an ideal. For instance, you can consider ideal generated by A. It's ideal of all elements of form AX, where X belongs to the ring R. So unity doesn't belong to this ideal generated by A because A is not invertible. So this is an ideal. It doesn't have unity, so it doesn't. It's not equal to R, but it is clearly an ideal because if you take something which is divisible by A, and these properties will be preserved. Okay, so this is the first observation, that you have lots of ideals in a ring if it's not a field. If it is a field, you have only 0 as an ideal, as we just discussed. So now the second observation, also very basic claim. If I inside R is maximal, so suppose it is an ideal, then I is maximal if and only if the quotient R over I is a field. Well, if it's not a field, then it contains an ideal, and you have a map from R to R quotient by I. This is a homomorphism of rings, and you have, if you have an ideal there, you can take its pullback preimage, and it is an ideal in R containing I strictly, so its I can be maximal. Conversely, if if the quotient is not a field, I is not maximal ideal, and if I is not maximal ideal, then the quotient is not a field because it has other ideal, which is bigger than I. Okay. So now we will discuss existence of maximal ideals. This is the first and last time I will use some set theory, but it's necessary for existence of maximal ideals, and also I would use it for some other things as well. Today, only today. Okay, so we have a partially ordered set. So order on a set is a relation, binary relation, partial order. If you have the following, if you have A smaller than B, B smaller than C, then A is smaller than C. It's the first. It's transitivity, I think. Yes. And non-reflectivity. So sometimes you consider this is called strict partial order. Sometimes you allow inclusion. It's like A is less or equal than A. You write this. But here it's strict order. So non-reflectivity is that A is not equal, not less than A. This is something everybody knows. For instance, for reals, for integers, they have this order. And partially ordered set is also called poset, partially ordered set. And there is, of course, this is something slightly worse than typical what we have. For instance, we can have things like you have point, 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 And then this bigger, let's say this A, B, C. B is bigger than C. A is bigger than C. But it's not clear whether A and B are related. There's no relations between them. None of them is bigger than another, because it's partial order. So non-partial order, like total order or linear order, suppose you have a set with partial order relation, is totally ordered or linearly ordered if for all x and y inside A, x smaller than y, or y smaller than x, or x is equal to y. One of those three things should be true. It's like the order on reals, on rational numbers, on integers. If you know ordinals, this is how the ordinals are ordered, and so on. Now I'm stating certain lemma. I'm not going to prove it, but it is an important lemma which is always used in math, like every time, even in algebra. Zorn was algebraist himself, and he stated this Zorn lemma in something like 36 when he was, I think, about 20. Maybe 23 or 25. I think he used this precisely to prove existence of maximal ideals. So Zorn lemma. I think he was a student of Krull and worked in Germany at the time, but he immigrated to United States almost like in mid-30s, about the same time as he proved this theorem. So let S, this partial ordered set, and suppose that for each, I forgot to tell you one more part of the definition. So X inside so definition, X inside partial ordered set is maximal if for each y inside S, y is not bigger than S. Then it is maximal. In partial order, again, with this picture, when you have this is bigger than that and this is bigger than that, these both are maximal, and A is not maximal. Okay. And suppose, in addition, that for each subset, S1 inside S, which is linearly ordered, in the sense that you restrict your partial order to S1, and it is like with these two subsets. I mean, the subset of consisting of A, B, it's linearly ordered. There is C and A, C or B and A, doesn't matter. This subset is linear ordered, and if you include B, it's not linearly ordered, because you can't compare B and A. So suppose you have for each S1 inside S, linearly ordered, there exists small s, also in S, such that S is bigger than all S1, all S prime inside S1. Then S contains maximal element. Generally, you can have no maximal element. For instance, consider reals. There's no maximal element. Consider natural numbers. There is no maximal element. So existence of maximal element is non-trivial. Something is missing, yeah.
defined it like non-reflexive. So it is. So your order is like more strictly more, right? And I mean, you want every linearly ordered set to have a upper bound.
Yeah. Yeah, you're right.
Equal of-
Yeah, of course. So it could be equal. It's bigger or equal because it might be contained there. Thanks. You're right. Sorry about this. Good. So the problem is here is that Metin noticed that you have to, if you take all of them, then this would make no sense.
Consider, for example, your set. So consider your partial order a set of all subsets of some infinite set, right?
Yeah.
And
You-
it satisfies this condition. So linearly ordered subset
Yeah.
is a subset of nested sets, right?
Yeah. So you should.
Every has an upper bound. Just
Mhm,
right?
mhm.
But what is the maximal element there?
Yeah. So you need to have this. S is bigger or equal. There exists one which is bigger or equal. Then it is.
It's still satisfied. So like any linearly ordered set, that is set of nested subsets.
You can take all of them.
So that's okay. That's maximal element.
Yeah.
Because like for ideals, we
Yeah.
don't consider
Yeah.
everything as an ideal.
Yeah. So let's. I'm not going to prove it, but I'm going to use it to obtain bases in vector spaces and to obtain ideals in rings. So first, bases. It's a linear algebra which everybody should sort of know by now, but still. In that generality, not many people know what it is. Sometimes it's also called the basis in the sense of Hamil or Cauchy. But I think by now it's just commonly called basis. The problem is that sometimes you consider topological vector space, and then the basis is different thing because it's something related to topology on the vector space. And here I consider vector space without any topology, so the notion is slightly different. For instance, in Hilbert spaces, bases are not bases in that sense. Okay, so definition. Suppose V is vector space. S inside V a subset is called linearly independent. If for any linear combination so when I say linear combination, I take the sum, it's vector space over the base field K. And I take a sum of vectors with coefficients in K. So it's like AI, VI, where SI are vectors inside the set S, and AI are elements in the field K. And this is finite. So when I say linear combination, I always mean this kind of sum. So if it is equal to 0, if is equal to 0, then, yeah, and all SI are different. So are distinct. So SI are distinct. You're not allowed to take the same SI twice. So if this is 0, then all AI are 0. This is standard. Now define
SI should be not only distinct but linearly independent.
yeah, this is definition of linear independent. Thanks. No, it's a legitimate question. So this definition of linear independent set. If when all these sums are 0, then all AI are 0. Okay. So now definition. Linear independent set, S inside V, linearly independent. Independent set is called basis if for each V inside this vector space, V is a linear combination of elements from your S. Okay. AI, VI. So, oh, SI, where SI belongs to S. So basis is a linearly independent subset such that each vector can be expressed as a linear combination of vectors inside this S. So this is the same as a maximal. So remark. Well, suppose it's not maximal. Then what is maximal? Maximal is when you can add, when you cannot add one more vector so that the whole thing remains linearly independent. So you have this set S. If it is a basis, then all elements of V are dependent. I mean, they can be expressed through S, so you cannot add one more vector to S such that the whole thing remains linearly independent. Conversely, if you have a linear if it is maximal, then it is a basis. Otherwise, if it's not a basis, this means that you have a vector which can be expressed through elements of S, and then it is not not maximal. You can add it, and S increases. So basis is the same as maximal. Now let's prove existence of a basis. This is one of the applications of Zor lemma. And proof. You applied Zor lemma to the following partially ordered set. So you consider the set S. It's a set of all linearly independent subsets of V ordered by inclusion. Okay, so now how, let's check the proper, how you can apply Zor lemma. So the partial order, I think, is clear. Just one algebraically linearly independent subset is smaller than another if it's strictly included into that other set. So maximal are really maximal. They are bases. Now, Zor lemma is can be applied when you have a sequence or just a chain, maybe indexed by some even continuous subset. So you have a chain. Si goes to Sj. Could be any set.
Why it's not empty?
Sorry?
Why it's not empty?
S is not empty.
It's obvious.
It contains empty set. But it contains also any element of one non-zero vector is linearly independent on itself. So it contains at least elements S contains elements which are like singletons of one vector. Or also it contains empty set, which is also there, because empty set is linearly independent. But then you have one vector, you can add another, and do it ad infinitum. OK, so suppose you have a chain of linearly independent subsets. Take its union. Suppose it has a linear combination, sum of AI, Si, which is 0. Finite linear combination. Each of these Si belongs to one of this linearly independent subset. And they're all included. So one of them belongs to the biggest one. And then all of them belong to the same set. And they're linearly dependent on that fixed set, like S n. So this relation cannot hold not only in this Sn, but where all Si belong to this chain somewhere. So this implies that the union of all Si is also linearly independent. It is a maximal, it's bigger than all of them. So you can apply a Zorn lemma, because for each chain you have an element of your partially ordered set, which is bigger than all of them, bigger or equal than all of them. OK. Then you can apply Zorn lemma, find a maximal element, and as we just discussed, maximal elements are the same as bases. Am I? OK. Now we can ask about what about dimension? We know about finite dimensional spaces, the dimension is well defined. So let's define the dimension is cardinality. So if you have V vector space, dimension of V is cardinality of its basis. So cardinality of a set is two sets have the same cardinality if you have bijection between these two sets. And sets are actually ordered by the cardinality. If you have two sets, you can always embed one into another, which is non-trivial consequence of axiom of choice, but it's really, intuitively it's clear that every two sets, one is bigger than another. So this set of possible cardinalities is actually ordered. And the claim, if you have two bases, S1, S2 are bases in V, I think grammatically correct is to say basis, but nobody understands this. Two bases in V, then cardinality is denoted by this. Cardinality of S1 is equal to cardinality of S2. For finite dimensional spaces, everybody knows that. And for infinite dimension, I think it's a good problem which you can try to solve. I won't go into to tell it, but it is, if you know a bit of set theory, it's really pleasure to solve this problem. OK. Oops, sorry. This was a picture of Zorn, but before I'm going to show you this picture, I'm going to tell you about maximal ideals. And the proof is almost like identical to the proof of existence of a basis. So theorem. suppose you have I inside R is ideal in a ring, then I is contained in maximal ideal, where M is a maximal ideal. And the proof, consider again per set of all ideals in R ordered by inclusion. And apply Zorn lemma. Of course, to apply Zorn lemma, you have to again to check that it can be applied. So you have to check that if you have a chain of ideals, you have a chain of ideals, maybe like I1, IK. It can be infinite. It can be ordered by something like R, by some very strange set, but it's totally ordered. Every ideal is included to another. Then the union of all these ideals is also an ideal. Well, it's sort of clear that if you multiply element of this by an element of a ring, or if you add two elements in that chain, you obtain an element of that chain. But what is slightly less trivial is that it is not everything. So need to check that this union is not R. So it doesn't contain unity. This is what we need to check. But suppose it does contain unity. Then we have unity is equal to sum of elements in these ideals. So it's Ri, where Ri belong to these ideals. OK, it's a final sum. And the ideals are ordered by inclusion. And again, you can take the maximal of these ideals. It contains the whole of them. So this thing actually belongs to some biggest ideal. Ri belongs to In. All of them belong to the same ideal. And then the sum belongs to the same ideal. The unity belongs to this ideal, which is impossible because this is an ideal. And we don't allow ideals to contain unity. OK. This proves that we can apply Zorn lemma. And this implies that we have maximal ideals containing every ideal. OK. So for now, you take the partial ordered set of all ideals containing I, of course, because you want your maximal ideal to contain I. And of course, maximal ideal in the sense of Zorn lemma is the same as maximal ideal in the sense of this as we defined, because we order ideals by inclusion. OK, this is a picture of Zorn. So he immigrated to the United States. He worked in Caltech. Then he moved to Indiana. And this is a picture which actually I was in Indiana University. This is a picture which is hangs in their common room. OK. So Hilbert didn't do much in algebra. Most of his work were, well, he did lots of number theory, analysis, and geometry. But in pure algebra, he essentially had one paper which contains everything. So you see, it's paper about invariance. This is the Uber de Wollen invariant system, полный system about complete invariant systems, complete system of invariance. It's a paper about when you have a group acting on a vector space, you are interested in polynomial invariants, polynomial functions which are preserved by this group, or tensors which are preserved by these groups. And he explained that it's possible to write down a basis of these tensors and express the whole invariance through this basis. which sort of solved the long-standing problem because people did that for particular vector spaces and particular group actions and spent like hundreds of pages writing down these invariants. So Hilbert killed this part of math entirely. People were very angry with him. He was very young. I think he was 20, maybe 27 when he wrote that. And in particular, in addition to the standard results of Hilbert, like Hilbert basis theorem, this also contained the Hilbert-Nur-Stellensatz, which is a theorem which allows us to build rapport, to build relations between algebra and geometry. So this is a central theorem of algebraic geometry. This is a starting point of algebraic geometry. So this theorem tells us that there exists a correspondence between maximal ideals in a quotient ring of polynomials and the points in algebraic variety. So there's a bigger versions of this theorem which I will explain next time, namely why the ideals correspond to varieties. This is also true. But today I will speak only about maximal ideals. It's still very interesting. So theorem. Yeah, there was something on slides which I forgot to tell you about. Maybe it's a good moment to return to it and repeat. The example of maximal ideal. I think it was there. No, sorry. Yeah. The example of a maximal ideal was there. And this is an important example. So suppose you have a affine variety. You have an affine variety A. This is the same as a subset given by a sequence of by a system of polynomial equations, and you have a point in it, and you have a ring, or A is a ring of polynomial functions. Consider the ideal of all functions vanishing in this point. So f of A is equal to 0. Then IA is maximal. It's called maximal ideal of a point. Okay, proof. So for each f inside this ring, you consider a function f minus f of A. It belongs to this ideal, right? Because it vanishes in this point A. But this is constant. So this means that OA is equal to I. So the quotient is projected to C. Yeah, it's embedding and also it's surjective. This is an isomorphism. Because every up to a constant, every function belongs to IA. So this means that you have this map, just f goes to f of a, and its kernel is precisely this ideal, and its image is C. So this is a maximal ideal. The quotient is C. So the Hilbert-Nordstein Satz tells us that there is no other examples of maximal ideals. You suppose you have a maximal ideal, M inside OA, where OA is algebraic functions, polynomial functions on A, which is algebraic variety, maximal. Then M is IA, is a maximal ideal of a point. There's no other ideals except maximal, except ideals of a point. So maximal ideals are always ideals of points. There is a bijection between points and maximal ideals, and this allows us to treat the maximal ideal geometrically and to build the relations between geometry and algebra very nicely. Okay, so the idea of a proof. Okay, the idea is the following. You consider this quotient, or a quotient by this ideal, maximal ideal. It's a ring. Well, it's actually a field because it's a field. But it's a quotient of polynomials. Of polynomial ring C of x1 dot xn. Because this is a quotient of polynomial rings. I mean, these polynomial functions, so they are generated by coding functions as a ring. So it's countably dimensional. So as a basis, you can take a maximal subset in monomials, which are linearly independent. You start with a monomial. You check if it's linearly dependent on the previously chosen monomials. If it's linearly dependent, you don't add it. If it's linearly dependent, you add it and go to the next monomial. And this you do, you repeat that, and then you obtain a basis, and this is a basis of monomials. So it is countably dimensional, because it's generated by monomials. And then you prove that no field containing C, well, strictly containing C, So you have K, which is strictly bigger than C, is countably dimensional. So if you have a field obtained by adding something to C, it's always either C or its dimension is continuum. And this implies that you cannot have this implies that this field, the quotient field by maximal ideal, is just C. And if it is C, you produce a point very easily. Like, it's essentially a tautology, how to prove that if the quotient is C, then the ideal is the ideal of a point. You will see it. Okay, so this is, I think, the picture of Hilbert at the more or less the moment when he proved it. Well, maybe a couple of years earlier. Before I go on, I would tell you about dimension of the field of rational functions. The point is that, okay, suppose you added and next you increased your ring, increased your field of complex numbers. This means that you added an element to complex numbers. So you added t, and this gives you c of t, quotient by something, maybe by some ideal. If you have any polynomial relations, this gives you a quotient. On the other hand, this means that t, so every ideal in c of t is principal, because it's principal ideal ring. So this is a quotient by polynomials. But every polynomial of degree bigger than 1 is reducible. So this you can easily see that this can happen that only if by the main algebra theorem, this will be equal to c, and t will be equal to some a inside c. Otherwise, this quotient is not a field at all. It's a direct. It will have zero divisors. Indeed, suppose that p of t is not degree bigger than 1. Then it's a product. P of t is equal product of t minus I mean minus ai. There are roots of p, and then you take t minus ai, their product is 0 in this quotient ring, and then there are 0 divisors, unless they are all 0. All, unless one of them is 0, and in which case we have this. So this was a very short explanation of why if you have added if you have a field, so suppose you have a claim, you have a field, say K, containing C, then K contains the ring of rational functions as a functions of form P of t where by Q of t, where P and Q are polynomials. This is called the field of rational functions. I guess everybody should know what it is. And so T is either algebraic or transcendental. Transcendental means that it is never a root of any polynomial equation. And algebraic is that it is a root of polynomial equation by this argument. Since C contains roots of all polynomial equations, then it is just equal to its root. The quotient is a field. So C has no algebraic extensions. And this is why every element which belongs to K and doesn't belong to C is actually transcendental over C. It is not a root of polynomial equation. But then this means that you can, this is all non-zero, where Q of t is non-zero. This is non-zero element of this field, and you can take a quotient. So this is why any field which contains C contains strictly contains C, contains rational functions. So we're interested in rational functions. This is why I'm going to tell you about rational functions now. So lemma 1, C of t, this is the field of rational functions, is continuum dimensional. As a vector space over C. Of course, this is a field itself. So over itself, it is one-dimensional. But over C, it's a really big space. And it turns out that it is even continuous dimensional. So that big. OK. So how we prove that it's continuous dimensional? So first, it cannot be bigger than continuous dimensional because it's continual. I mean, what is this, guys? They're quotients of two polynomials, but each polynomial is given by a set of elements in C. And this, so the set of polynomials has the same cardinality as C, and this quotient has the same cardinality as C. So it can be bigger than continuous dimensional. And to prove that it's continual dimensional, we need to produce a subset which is continual and linearly independent. So lemma 1 is proven by enough to show that all elements of form 1 divided by t minus a and c, are linearly independent. This would give you a set, linearly dependent subset in this field of rational functions, which is continual because A can be chosen in C. There's precisely continuum elements in C. In fact, I think you can prove that this is, it's almost a basis. To make it a basis, you just need to add things like t minus a power k. And then it becomes a basis. But we don't care if it is a basis or not, because we already have upper estimate, and this gives lower estimate on cardinality of a basis. OK. Good. So let's prove it's linear independent. You have us form a relation. Sum of lambda I divided by t minus ai is equal 0. Let's prove it's impossible. To do that, you multiply it by the product. So it's from I equal 1 to n. You multiply this relation by the product of t minus a over all from I equal 1 to n. So if you multiply them, you obtain sum from I equal 1 to n, lambda I, t minus a1, dot, 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 t minus ak from k equal to 1 to n, where this is omitted. You don't have this particular multiplier in this product. T minus ak plus 1, dot, 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 t minus an. So this was n, so it's n minus 1 dimensional polynomial obtained by product of these linear functions. And you apply that to, say, so let's call this p, or did we have p? No, it has, let's call this p of t, it's a polynomial, and we apply p of t to a1. And we notice that there's only one summand in the sum which doesn't have t minus a1. So it will be a product, lambda 1 times lambda 1 times a product of t minus ai from I equal 2 to n. So there's only one term where you exclude t minus ai, which appears in that. And here you have a1 instead of t, of course. And this is non-zero. So this polynomial is non-zero in a1. It can't be 0. So this linear equation is impossible. And this implies that you really have a continual basis in the set of rational functions. OK. So now we're almost done with Hilbert-Neustein Satz. So Hilbert-Neustein Satz is there. It says that if you have a maximal ideal and a ring of polynomial functions on an algebraic set, then this maximal ideal is maximal ideal of a point. So I'm going just to produce this point in the end. But so the first observation is that it's enough to produce common zeros. So step one, enough to find A inside C, inside our algebraic set A, such that all P inside this maximal ideal vanish on A. Because in that case, this maximal ideal belongs to IA. Well, it's maximal, this is maximal, so they're equal. So if we find the common zeros for this ideal, we're done. All we need to find is common zeros. Step two. OK, so we know that quotient, or A quotient by I, is a field, which contains C. Because it's a field which is also a vector space over C, so you take unity, you multiply it by elements of C, obtain C inside this field. And all T inside this field so we take this field without C, which sits there, is transcendental. Because all algebraic elements over C belong to C, it's algebraically closed. It's something I tried to explain already. And this means that K contains the ring of rational functions. Which is continuum dimensional, so this means that K is continuum dimensional. Unless, of course, K is equal to C, which is also possible. OK, it cannot be continual dimensional because it's generated by polynomials. Polynomials are countably dimensional. So this implies step 3, then K, which is again OA by I, is equal to C. Okay. So, then what happens now is essentially a tautology. Let me explain. So we return to the statement of Hilbert-Nollstein. Thus, we have a maximal ideal. It was denoted by I here. So we need to show that this maximal ideal is ideal of a point. For that, it suffices to prove that there are common zeros of these functions and that ideals. And this would follow from the isomorphism. So how to do it? We have a map. Let's call it phi. So the map, which goes from OA, from the ring of polynomial functions on our algebraic set A, to C, which is just you take, this is equal to OA quotient by I. The important thing that there's a bit of ambiguity here, because a priori we can have things like automorphism of C. What is important that this map is itself defined over C. It's a C-linear map because this C is a vector space over C, this OA is vector space over C, and this homomorphism is compatible with C acting on itself. This is because what we proved is that this quotient is actually one-dimensional over C in the steps 1-4. So this is a C-linear map. Okay. Now we have consider the sets. Let's apply that to coordinate functions. We have Z1, so our A belongs to Cn. We have Z1, Zn coordinates. This map, let's call it phi. So I have phi of Zi. Let's call it Ai. I claim that the point A1 An, which belongs to Cn, is common zero. Of our ideal. And this is what we need to show. We need to show that there is a common zero. This produces this common zero. How to do that? Okay, we have P inside. It's a polynomial, so it belongs to I, but it's a polynomial function. So you consider P as a polynomial in Z1 Zn. And then you evaluate it. So you take phi of P. How you evaluate phi of P? You just apply phi to all coordinates. So it will be P of A1 An. You just substitute phi of Zi instead of Zi. And phi of Zi is Ai. And this should be 0, belongs phi, because phi restricted to I is equal to 0. Phi is a map from OA to the quotient. So this means that P of A1 An is equal to 0. And this precisely means that what we want, that a1 dot an is common zeros of our maximal ideal I. And this finishes the proof. So this is sort of tautology which finishes the proof, but it is an important tautology. So before I finish today's lecture, let me give you an exercise for the home. I already mentioned this. So you have functions. Prove that functions are 1 over t minus a power k, for each k is equal to 1 dot 2 and so on, and a belonging to C are form a basis in the rational functions. This is a good exercise to understand what is a rational function. And what is a basis, actually. This is sort of semi-standard. In fact, many people do that even for real. So the same over reals. You have R of t. It's rational functions over reals. Over R. And here the exercise is that you take 1 over t minus a power k and 1 over p of t power k, where p of t is quadratic polynomial with no real roots. That these functions also form a basis. So this is a basis in real rational functions. You have, again, A belongs to R, K is equal to 1 dot 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 and dot dot. It's all positive integers. And P, real quadratic polynomial, so it's over R without real roots. Okay. This is home exercises. Just the next session, I think, is Thursday. And let me tell you what I'm going to tell next time. Well, there are two subjects which are important. First is categories. You have equivalence. Well, categorical language is a language which is used by mathematicians to describe relations between mathematical theories. For example, you can have two theories which are arise in entirely different parts of math which are equivalent. So here, Hilbert-Nurstein Satz is a statement about equivalence of categories. There's category of finely generated rings over C without nilpotent elements is equivalent to category of algebraic varieties. This is one of the subjects which I'm going to discuss next couple of lectures. Another subject is the following. There is a stronger version of Nurstein Satz. which says that suppose you have an I inside polynomials. It's an ideal of such that polynomials quotient by this ideal has no nilpotence. Nilpotence is an element which is 0 in some power, such that then this ideal is entirely determined by its common 0 set. So you take V of I, its common zeros, of I. And it turns out that you can reconstruct this ideal from the set of common zeros. This is one of the applications of the theorem which I gave. Just what I gave you is a special case of this more general theorem. And of course, it is used to produce this equivalence of categories. But of course, I didn't define categories, so I'm stopping now. Thank you.